This lesson is about hydrates. So first, let's talk about what a hydrate is. A hydrate is a substance that has water molecules loosely bound to them. Most of these are ionic salts. So a lot of the things that we've been talking about, things like copper chloride. So if you have CuCl2, oftentimes you're going to have water associated with this also. So remember, we talked about ionic compounds make this lattice kind of structure, right? And then these guys are all attached to each other. These guys are all attached, and then you've got atoms back here, here, and they're all attached to each other. Okay, so you make this kind of lattice. Well, what's interesting about these lattices is that there's space inside the lattice where water can go. And so that's kind of what happens to hydrates is you've got water trapped inside of your crystal structure. And so the way that we write hydrates, when we write the actual formula, is we write our ionic formula first, CuCl2. Then we use a dot, and then we indicate how many waters are present by using the dot. This means hydrate, not multiplication. And then a 5 or 6 or whatever it is, and then water after that. Okay, so this is one of the most classic experiments in a first-year chemistry class, is to do the percent water in a hydrate lab. So if we were in a traditional setting, then we would do this experiment in the lab. Since we are not in a traditional setting, what we will do is we will do a virtual lab, essentially. So you're going to watch a video of someone performing the hydrate lab, and you're going to take data from the video, and then you're going to use the data that was presented in the video to complete a lab report. Okay? So experimentally, we can determine the percent water lost from a hydrate by heating the sample to drive off all the water. That's the point of the hydrate lab. You start with a hydrate, and they look like wet sand. Okay, they're very moist, I guess, so to speak, because there's water. They're not a dry powder. It's more like moist crystals, like sand. Okay, and so after you heat it for a long period of time, then the water evaporates, and then you're left with what we call an anhydrous salt. Okay, so we do this. We must measure the mass of the sample initially. Then we heat it for about 5 to 10 minutes. Once it's cooled, we mass it again. Then we reheat it for about 2 minutes to ensure that all the water is gone. Okay, when all of the water has been removed, we call it an anhydrous salt. Anhydrous just means without water. Okay, so once all of your water is left, now you have an anhydrous salt instead of a hydrate. One of the ways that you can be confident that all of the water has been removed is when the last two mass measurements are nearly the same. We're talking like within 100th of a gram. So if you get 24.95 grams after your second heating, and you get 24.94 grams after your next heating, these guys are close enough together to say that they are constant. Okay, so what that means is you're not going to keep heating. You can be confident that all the water has left your sample. Okay, now let's talk about how we're going to name hydrates. This is an important part of this section. So hydrates have a dot between the salt and the number of waters attached. Unlike in math, the dot does not mean multiply. It simply means that you have waters loosely attached. It means that you have a hydrate. So this example, NiCl2.6H2O, is below. So to name the hydrate, you're going to name the salt first. You're going to use ionic rules. Okay, so if it's a fixed metal, you'll use fixed metal rules, right? And just name the first element, the metal, and then name the nonmetal or the polyatomic ion. Okay, if it is a transition metal, then you need to name it with Roman numerals. Okay, so that's the first step, is to name the first part of the salt. Okay, and in this case, we have nickel. And if you look to find nickel on your periodic table, you'll see it's a transition element. So we need a Roman numeral. And then we have chloride. I don't know why my pen messes up. Hang on. Okay, so now we got to check the charge. Remember, whenever we do this, we have to check the charge. So chloride is -1. We have 2 of them. So we're going to multiply by that subscript to get -2. We have to ask ourselves, what do we need to add to that -2 to equal 0? It should be +2. Then we check to see if there's a subscript here. Since there isn't, we're done, and it's 2. If there was a subscript here, you would have to divide by that subscript to get your answer. Okay, so the first part of this is nickel 2 chloride. All right, so then we go to number 2. Name the number of waters by using Greek prefixes. All right, so if I see 6 there, I know 6 is hexa. So I'm going to write 6. I'm going to write hexa for 6. And then you're going to tack the name hydrate at the end to mean water. So it's going to be hexahydrate. And there's no space there. So this would be nickel 2 chloride hexahydrate. All right, we'll do one more example. Actually, we're going to do 3 more examples on the next slide. Okay, so for this one, we've got manganese. Okay, it's going to have Roman numerals, and we know this is a chloride. Now we know the chloride is -1. We multiply it by 2 to get -2, so that means our manganese must be +2. So that's manganese 2 chloride. And we look and we see that there's a 4, that is a tetrahydrate. Let's do the next one. CO is cobalt. Also transition element. Once again, we have a Cl2. That's a very common salt for hydrates, is a +2 charge with a chloride. So cobalt 2 chloride, then we see that we have a 6 here, so that will be a hexahydrate. All right, one more example. For this one, this first element is sodium. I know it's a fixed metal, so I do not need a Roman numeral. And then SO4 is sulfate. So I have sodium sulfate. And then I look here, 10 is deca. So I have a decahydrate. And that's all it is. That's all there is to naming these. All right, now let's move on and talk about the lab that you guys are going to do. Okay, so in the hydrate lab, you're going to heat a hydrate in a crucible, which is a small porcelain container, until all the waters are evaporated from the hydrate. Pretty simple experiment. Crucibles, small porcelain, they kind of look like this. All right, and you're going to put the solid inside there. When all the water is evaporated, the color of the hydrate changes, and you're left with an anhydrous salt. Sometimes it gets lighter, sometimes it goes towards a white, sometimes it goes towards a blue from a purple. They're all different colors. I've seen them go from like green to orange. So the color that it changes to is not as important as the fact that it will change colors once the salt is becoming anhydrous. All right, so the real way that you know that you've heated the hydrate enough, though, is not just the color change. Your mass measurements must become constant. So generally, you heat the hydrate from 5 to 10 minutes, then you let it cool, because the heat surrounding your substance and your container can cause heavier air currents near the balance, and it causes it to make the mass greater than it actually is. So it's really important that you let it cool enough. Now, a lot of hydrates are what we call hygroscopic. Hygroscopic means that it is water loving and seeking. So what that means is it will take water from any sort of source that it can, including water from the air. So you've got to be really careful when you're doing this cooling process here that you don't let it cool too long to where water vapor from the air can rehydrate your sample. Okay, that is a possible source of error if that happens. Okay, so then you're going to heat it again for a couple minutes after you take the mass the first time. You want to make sure that all the water is off. So even though the color change has happened, you want to heat it strongly for another couple of minutes, let it cool, and then see if the mass has gone down dramatically again. If it has, then you have to heat it again until it's constant. Here is a setup for the heating apparatus. You'll notice that you have a crucible with a cover that is slightly askew. basically, you can't do this experiment. If you put the cover all the way on, then there's nowhere for the water vapor to go, and it will stay inside your crucible, and it will be kind of pointless. So you need to have a way for your water vapor to escape. However, if you leave it completely uncovered, sometimes if you heat it strongly, you can get hydrate to spatter out. And if your hydrate spatters out, you're going to assume spattered hydrate is water when you lose that mass. So that will make your percent water higher than it should be. That's if you have a hydrate splatter out, okay? If you don't get enough of the water gone, then your percent water is going to be too low, all right? So then you'll see that you have to prop this on what we call a pipe stem triangle, and it just allows your Bunsen burner flame to directly touch the bottom of your crucible to heat it faster and more strongly, okay? And then you know about the rest of this kind of setup. Okay. So now the important part about this is the calculations. So to calculate the water lost, you're going to subtract the mass of the anhydrous salt after final heating from the mass of the initial hydrate. Now, something you have to be careful about here is you're going to have the mass of the crucible also. Because when you measure the mass of your anhydrous salt, you're going to also be measuring it inside the crucible. So you're going to have to subtract the mass of your crucible from both of these measurements before you can actually get the mass of your water lost, okay? So once you have the mass of the water in the sample, to find the percent water, you'll divide the mass of the water by the mass of the whole hydrate. So let's say that you end up with 1.30 grams of water, and you started with 3.01 grams of your hydrate. Okay, this is kind of what I'm talking about. This is how you're going to do this. You're going to have your grams of water lost over your gram of your total hydrate times 100, and that's going to give you your percent water. Okay, now your task is going to be to calculate the number of waters of hydration. So to do this, you're going to divide the amount of water by its molar mass. Okay, so in this case, you're going to take, let's say you had 1.30 grams of water. You'll divide by the molar mass of water, which happens to be 1802 grams per mole, to get your moles of water. Okay, then you're going to do the same thing with your anhydrous salt amount. Okay, so, you know, in a scenario like this, where we had 3.01 grams of your hydrate, you'll subtract 1.30 grams of water to get your grams of your salt, anhydrous salt. So you'd have 1.71 grams of your salt. Now you're going to have to know what the salt is to find the molar mass of the salt. Okay, so that will be given to you. All right, then you're going to get moles of your salt. Okay, so just like when we found empirical formulas, you're going to have a mole amount here and a mole amount here. You're going to divide both of them by the smallest number of moles. Okay, so your mole of your salt should always be less than your water. So when you divide it by this should be 1, and then this will give you 5, 4, whatever. This will be your waters of hydration. Okay, now we're going to do an actual example with real data so that you guys can see what I'm talking about. All right, so here's a practice problem. So we've figured out the mass of the crucible. We also have the mass of the crucible and the hydrate. And then you have to find the mass of the hydrate. So you're going to take your mass of your crucible. You're going to subtract the mass of the crucible from your crucible and hydrate to get your mass of your hydrate. Then you heat it. After the first heating, you see that the mass goes down a little bit. Once you heat it again, it goes down more. And then when we heat it the third time, it doesn't go down enough to matter. You see these are very close. They're close enough to be called constant. Okay? So then it's time to figure out the mass of your anhydrous salt first. So I would do this one first. So you're going to take the mass of the third heating, the very last heating, and then you're going to subtract the mass of your crucible. That's going to give you your anhydrous salt. To figure out the mass of your water lost, you're going to take the mass of your hydrate, which we have up here, and you're going to subtract the mass of your salt, which you have here. Okay, so mass of the hydrate minus the mass of the salt, and that gives us 1.136. Okay, so this is how you would fill out your data table, and this will be available for you to go back and reference. I will post this PowerPoint along with this video so that you can reference the PowerPoint also. Okay, so now we go to calculations. So in this particular instance, they told us that our salt was cobalt 2 chloride, and we have to figure out how many waters there are. Okay, so we figured out how many grams of salt we have. Well, now that we know that it's cobalt chloride, we could find the molar mass of cobalt chloride. So we're going to take this divided by our mass of cobalt chloride to get this many moles. So that is cobalt chloride moles. We're going to do the same thing with water. So in our data table, we found out that we have 1.136 grams of water, and we're going to divide by the molar mass of water, and then this gives us moles of water. Now, to find N, which is what our big goal is, you're going to divide both of these by the smallest amount. Well, both of these, you'll see that the smallest one is the 0.0105. So if I take 0.0630 divided by 0.0105, I get 6. So my answer, what I'm looking for in my lab, is this. 6 waters of hydration, right? So that would be my answer. So when I'm reporting my answer and my conclusion, I'm going to say that I was able to determine that cobalt 2 chloride has 6 waters of hydration, and this should be the formula. Okay, so that's the whole point of the lab, right? The purpose of the lab is to find out the number of waters of hydration. Okay, so now let's talk a little bit about your lab report and what you need to have included. Okay, so lab reports have these major parts. And this is very different than a report you would write in English. Okay, so what you do first, you need a title at the top, and it could be something as simple as determining waters of hydration from a hydrate. Okay, so make sure you have your title, make sure that you put your name on it, put your name under it. Okay, and then when you go to fill this out, you are literally going to label each section. So the first section, after you have this, you're going to literally type introduction and underline it. And then under that, you're going to write your introduction in paragraph form. Okay, then when you get to the next section, it's materials and equipment. You're going to write down materials and equipment, right? And underline it. Okay. So for each section, you need the heading, introduction, materials and equipment, procedure, data table. All right, so that's the first thing you got to know. All right, so then we go through here. Your introduction should be a paragraph that includes the purpose. So this is just one sentence, guys. Your purpose is one sentence. One sentence. What is the purpose of the experiment? What are you trying to find? Okay, you're going to include background information. So for this lab, good background information would be, what is a hydrate? What is an anhydrous salt? How do you know that you have heated the hydrate long enough to get the anhydrous salt, right? That's the kind of stuff you want. Basic setup information. How are you going to achieve your purpose? Okay. That all should just be about a paragraph, maybe 2 tops. All right. Then you're going to go to materials and equipment. You're going to bullet these. Okay. So you're going to say like bulleted list. So like Bunsen burner, ring stand, right? And then you can reference the diagram that I put in the notes, which gives you a lot of the equipment that you need. Okay. Don't forget to put that you need a hydrate. Okay. When you do the procedure, you need to make sure that you list these in steps. Step 1, do this. Step 2, do this. Step 3, do this. And what I would do for the procedure is try to jot these down as you watch the video of the person actually doing the procedure. Okay. Next is the data table. You're going to do one very, very similar to the one that I showed you in this note packet. Okay. Except for you're going to enter your data instead of my data. All right. The calculations are going to be the ones shown in the previous slide. Okay. And you can lay it out just like that. Tell me exactly what you're doing and then do it. Okay. And then you're going to have a conclusion paragraph. And that reiterates your answer. Remember, your whole point is to figure out what your water of hydration is. The salt that you are going to use is copper 2 sulfate. Okay. So you're going to try to find out how many waters are in copper 2 sulfate. All right. You want to list any sources of error that could affect your result, and then how to minimize your error. What could you do differently? Okay. A lot of times, if you heat these too much, you can decompose your sample. If you don't put on a lid, splatter could come out, and then you would assume that that's water, and that would make your water of hydration too high. If you don't heat it long enough, your water of hydration might be too low. Okay. So those are all things you need to consider when you're doing your lab report. You're going to get a couple days to do your lab report. Please type it by all means and then submit it. And then I'm going to also hold a Google Meet on Tuesday, I believe it is. It's on the schedule for you guys in case you have any questions. Okay. It's either Tuesday or Wednesday. I'm not sure which day it is. So please feel free to make sure that you contact me. If you have any questions about how to format your lab report, any questions about what should be in your lab report, or anything like that. Okay, thanks, guys.